Hi, welcome to Vortrix Results Part 2. This is chat number 10. This is for Patreon members only. Sebastian commented on the last release, basically wondering whether the equation that I showed for new electromagnetism was for protons or for electrons or for both. And from this I deduced that I need to show more of my hand on this right now. So that's what we're going to do. Okay, again, this is for patrons only. Do not talk about this with anyone else until after the Vortrix algebra paper is released. Okay, this video is going to get a little bit mathy. Don't be intimidated. The purpose is to connect the dots with some of my patrons who have engineering math backgrounds. Because basically what I need is a sanity check of sorts. And the math that we're going to be used in here is actually very basic. It would be from a, it'd be very basic from the point of view of a Bachelor of Science degree. So I know Lori or Sebastian or Tibor should have no problem. Maybe they forgot about this math since college, but it should be no problem for them to pick it back up again. Forgive me, my sleeves are a little wretched here. I'm wearing two sweatshirts to keep warm. Okay, the following sequence of slides is going to be part of the introduction video when we release the Vortrix algebra publicly. So this is going to be kind of the intro slides, and I'm getting ready for the Vortrix release in 6 to 8 months. Right now we have a lot more work to do in Vortrix algebra. I've got to get the paper written. I've got to try to get it published, and when they reject it, then I got to start developing. I don't want to release the Vortrix algebra until we have a halfway decent new electromagnetism model based on it. And 6 to 8 months, it probably won't take that long. I'm just giving myself a little margin because stuff always takes longer than I assume. Okay, so the way this video, this introductory video is going to come out, we're basically going to say that vector calculus is a lie. Now this is a little bit of an overstatement, but it's more for shock effect than anything else. And the way it's going to go on is say, well, in order to call something calculus, you need to be able to take a derivative. In order to take a derivative, you need to be able to compute the limit of an expression or function. And this is what a limit looks like. Now, I'm running into a problem with my Microsoft Office. Microsoft downloaded a patch to something, and now my equation editor doesn't work. And so I'm having to cut and paste equations from Wikipedia and stuff. It's a pain in the neck. But this is a limit function. This is what's used to calculate derivatives. You need to be able to take the limit as something like dt or delta t goes to 0. If you can't do that, you can't do calculus. Okay, in order to do this, you need multiply and divide. Okay? Classical vector algebra has no divide operator and no complete multiply operator. So this thing called vector calculus is a misnomer. And I'm going to show you it's essentially a kludge of one-dimensional calculus. And that's the reason, if you didn't learn in your Bachelor of Science degree, that's the reason why partial derivatives are all over the place. They're not full derivatives, they're partial derivatives. And if you've ever seen the equations, again, I cut and pasted these from Wikipedia. That's why they look all fuzzy, because they're just expanded bitmaps. Here you have the del operator, which is a bunch of partial derivatives. You can tell the partial derivative from this Greek symbol, which looks like a backwards 6. I forget what that's called, but they're using that as opposed to the normal. When you take the derivative, something would be d dot dx would be the full derivative. This little weird shaped curly d, if you want to call it that, means that's the partial derivative. There's the del operator, there's the gradient operator, there's the curl operator, and there's the divergence operator. And if you go through vector calculus, you'll find it's all partial derivatives and therefore all partial integrals. Now, what is all this partial stuff? Well, because you can't do multiply and divide with vectors, you can't take the limit function. And so the only way they've been able to affect a vector calculus is to take the one-dimensional vector or calculus, which we can in one dimension, we can do multiplication and division, and just make it so that whenever you take the derivative along a vector, as long as all the other dimensions aren't changing, then it works. But once you have interoperability between the dimensions, then you can't do vector, you can't take a partial derivative. And that's what that means. This means that we're using one-dimensional derivatives in a function of a vector where along that dimension, nothing else changes. Okay, so we basically cobbled together a whole bunch of one-dimensional calculus and called it vector calculus. But they've been honest. At least they used an operator and said, well, this isn't real. This is a partial derivative. And the use of the partial derivative operator. So at least they're honest about it. So all this really is not vector calculus. It's partial vector calculus. And this is why I did all this work on Vortrix algebra. Vortrix algebra is a complete vector algebra that contains a multiplication and division operator. Okay, and the reason why it's called Vortrix algebra is because one of the operands breaks down into a vortex matrix. And if you take vortex matrix and put it together, that's where the term Vortrix comes from. I'm not discussing Vortrix matrices here. That will be when I release it. You know, I need to keep something secret here. Okay, and because we can do multiply and divide, we can take the limits of vector expressions for the very, very first time in human history and do real vector calculus, not partial vector calculus. And let me show you an example of what I mean. Let's take the limit of a function. Let's choose, I don't know. Let's choose, let's say the left divide of R into the vortex matrix of VR direction. So what we're going to do is we're going to take the limit. We're going to substitute this into an expression and then take the limit of that expression as delta t goes to 0. I'm going to use dt instead of delta t because when you have to write a lot of delta t's, it's easier just to write dt. So when I use dt, I'm really using delta t. Okay, now how do we do this? Well, this is one thing we also learned from Vortrix algebra is that in order for something to resolve to a vector, it's got to be it's got to be an odd product. You know, there's a product of 1, 3, 5, 7 vectors. Odd products result in vectors. Even products result in Vortrix matrices. I'll just say matrices for short. Okay, so here's the expression I'm going to pick as my example of, this is the magnetic field, you know, the field effect of a proton that's moving through space, and this is how it affects the space around it using in Vortrix algebra. So let's apply this to the limit function, which I showed before, but now there's 3 in a row, so this is not going to be a chain rule, this is going to be a triple derivative. Okay, and even in standard calculus, they only show you in the tables a derivative for 2 variables. This is 3. It's okay. We just got to use the basic definition of a derivative, and we can do this. And so, what do? Well, we're going to do the expression that the function of all these 3 variables, a, b, c, whatever, plus the derivative of those times delta t minus the function of those divided by delta t or dt, and take the limit as delta t goes to 0. And that's how we're going to take the derivative of this. And so we got to do this, and we'll do this right now. So let's do this first part. And we take the r plus the derivative of r times dt, and that is left divided into the matrix V, which would be V plus acceleration, that's the derivative of V times dt, multiplied by R plus R derivative dt. Okay, and then we're going to minus this function. Divide all this by dt, and then take the limit of this as dt goes to 0. Okay, it's not that hard. It's really cool how this calculus works for those people that never learned it. This is really clever stuff. This was invented by Newton, but obviously somebody else decided to say, no, they invented it too. There's a big fight over who invented it. I think Newton's got the ball on this. So, but now, because we've got complete vector algebra now, we can apply vector algebra to develop a true vector calculus without the partials. This is the real deal. Okay, so now what we need to do is we need to simplify this by multiplying, what you would typically do, multiply top and bottom by this equation here to cancel it from here and get rid of this little division over here. But one thing in Vortrix algebra is that if you have a left divide is eliminated by a right multiply. So the top of the equation, we're going to do a right multiply of this. Okay, but we can't right multiply the denominator by that. We got to left multiply the denominator by this, and that was the thing that took me the longest time to resolve. Is that in the reciprocal operations, you know, if you have a right multiply, that's canceled by a left divide. Right multiply, a left divide, and a left multiply is canceled by a right divide. Okay, so a top left is canceled by a bottom right. So that's what we have to do. So we're going to right divide the denominator here, because obviously, you know, if you got a over a, you know, that's 1, and a over a is also 1. So we're basically multiplying this expression by 1. That's essentially what we're doing. Okay. So now what we're going to do, this cancels this, and we're left with this expression on the top. Now let's multiply that out down here. We have v plus r, vr plus vr dot dt plus a r dt. I'm pushing the a out because the dt is a scalar, so I'm moving that to the outside. Plus a r dt. Okay, minus, well, this first multiply here, this right multiply of r cancels the left divide of r, so that just leaves this as a vr. And then this guy here works out to that this guy would cancel this, and I'm going to just do it quickly here because if I try to explain it, I'm going to take all day. So we got v, okay, divided by r, okay, this, and then we got this, and that's what we got left here. Okay, and then our denominator is r dt plus r dot dt squared. Now, this guy cancels with this guy, and that leaves a dt in everything in the numerator, so we can, and in the denominator, so we can divide through a dt in the top and in the bottom. And now we're going to take the limit as dt goes to 0. There's only one dt left. That means this expression goes to 0. And what we're left with is, we got to right divide r on all these. So we got to right divide r into vr dot plus right divide r into ar direction plus right divide r ar dot and minus direction v. Now v dot is the velocity of the target minus the velocity of the source, and we've got our right divide. I already put the direction for the right divide up there, which gives us an r squared in the direction in the, and let me start a new page here. Oops. Out of paper. And so what we're going to do now is just take the a to the outside, and when you divide the vector by its direction vector, you're left with a over r direction. There's your new induction. And then you have two other terms, which I'm not really sure what they mean yet, but they're more vortices than anything else. Okay, and what we're left with, this looks like Coulomb's model, but with a wrong sign. This looks a lot like new magnetism, and I think that's a wrong sign. This is new induction with a wrong sign. That's a plus there. And we have two new terms, which are complete vortices. Because what this says, you have R, the direction vector of R, the derivative of the direction vector of R, which means it's not anything to do with the magnitude, so the only thing you could have out of this is a rotation. So these are vortices. I got to get to understand what these are some more. These are new things I've never seen before. Okay, but we have a lot of the elements of new electromagnetism derived from what would be a guess at a pretonic field equation. But again, we're not putting these into a second order system of pretons. So, where are we going with all this? I'm showing you that what we're going to do in the future is we're going to come up with a whole bunch of different guesses using a computer to permutate all the possible different ways we could come up with a second order system of pretons. The number of pretons, the number of orbits, the types of orbits, everything. We're going to come up with a permutator that could come up with every possible model, just what we did for new induction. Once we do that, we're going to have another permutator that is going to come up with every possible Vortrix expression that would be the pretonic field model. And again, just when we started this derivation over here, we started with something simple, just a single charge moving at velocity v. That's all we started with. And we're able to come out, when we took the derivative of this, we were able to come out with stuff that looks a lot like new induction. New electromagnetism. But the point is, there could be infinite numbers of ways to guess this, and that would give us infinite number of outcomes here. And is there a guess here that would give what new induction, new electromagnetism is? I bet you there is. There's got to be. Okay, and so what we're going to do is then we're going to have this come out with and see if we can't match new electromagnetism in vector algebra form. NEVA. New electromagnetism in vector algebra form. So what we need to do first, that's my purpose of going down the railgun project and then having to break into the paradox, is we're trying to make sure that we can get all the different terms of new electromagnetism. Because the little guess that I did before, where did I do with it? Oh well, I lost it. I think the guess. Well, it was in the last video. I don't know. I get all my papers mixed up here. I did have it here somewhere. But anyway, we came up with those three terms for new electromagnetism, which I believe is minus R, A, R, son of a gun. Oh, here we go. I found it. Minus VSR VT over R squared plus VSR VS over R squared. So this is what my guess is, because what we need to do now is we need to verify this, our endpoint. We need to have a valid endpoint for this before we can go and build all of this. This is going to be all software. And this, we need to validate this, or basically go through and make sure that we've got everything accounted for properly. And this shows that there's this guy here shows us there's other terms of magnetism that might be there that we're missing, because when we do the vortex diagram for classical, for new electromagnetism, which was mostly from classical theory, we got a lot of overlap. We got a lot of excess, so we got some things that look like they're missing. Okay, this makes more sense to me as an amplifier, but we have to validate this. We have to go and make sure that this guess here matches all the things we can measure. We're already good with this guy, that's Coulomb's model, no problem. And we're already good with this, that's new induction. And so we need to batten down this guy. Once we have this, now we have an endpoint for this search, for this two permutation search function. And we're going to find every possible combination of pretons and the way that they orbit each other. You know, and that's a lot of variables there. You know, what's a pretonic basic charge? Is there up to millions of pretons? I mean, we're going to limit it at first and see where we get. And then what all the different possible Vortrix expressions that could explain the simple magnetic field, the simple pretonic field, and then take the derivative using numerical methods, and then see if we can't match what NEVA is. Okay, but right now we need to get NEVA. That's our important goal right now. We need to get new electromagnetism expressed in a Vortrix algebra expression to give us an endpoint for all of this. Okay, this is a lot of work, so bear with me. But we're making progress. Anyway, that's all I got for now. Again, this is only for for Patreon. I almost said Preton. For patrons, and thank you much for being patient. You'll have another update in about a week where we are. And I'm going to start, while I'm doing all this other work, I'm going to take the low-hanging fruit, which is the new version 4 of the rules of acquisition, start getting those out there. And there was something else I wanted to put out. I forgot what. Oh, and I'm going to put out the final video for Paradox 1C, and I'm going to show you a logical derivation that shows that I'm not going to run the experiment 1C because I'd rather continue on with this, because ultimately when we're trying to find the secrets of the unit, we've got to go to where the models diverge. Okay. And Paradox 1C, if I could figure out how to measure where the energy is in the Paradox 1 experiment, is it in the spinning disk or it is in the closing path, that would prove one or the other. But we don't have to go there. That's difficult to do. I can't figure out how to do that. Not with anything simple. I want to do it with something simple that somebody else can build. I found a logical way to say it can't be the classical theory way. That may not be satisfactory for some, but it's satisfactory for me now, because ultimately with all this new stuff, we're going to find another part where things diverge, where we can go out there and it might be easier to measure out here. And then that would prove this guy experimentally. So right now this is slowing me down. It's low yield. Okay, we need to go someplace with the stuff which is going to be high yield and either prove it one way or the other. So that's why I don't want to hang myself on this, because what we're doing is limiting ourselves to only one way to prove this. I want to go somewhere else where we can make forward progress and be able to eventually prove this later. So right now I'm going to hang on that the logical explanation is good enough and just bypass it for now. So I hope you are with me with this, and I hope my engineer patrons understand where we're going and why I'm all hell-bent on this Vortrix stuff, because we're fixing calculus for once. We're actually moving. It's sad that I just can't do my job. I got to do the physicist and the mathematician's job. So whatever. I do whatever I need to do to get this thing done. Thank you very much for all my patrons. I appreciate you all. And I'll see you probably in about a week. Oh, there's a guy out there. He wants to do an interview, so I'll probably be interviewing with him, and I'll give you links to his video that he's already done on one of my videos. Anyway, take care. Bye.